Hello everyone, welcome to the third tutorial of Signals and Systems. In this tutorial, we have questions related to invertibility of systems and systems defined in terms of difference equations or differential equations. So the first question says, consider the following system where h is yt, integration minus infinity to t, x tau d tau, that's an integrator, and g is a time compressor of sense because it gives output yt as x of 2t if xt was the input. So the first question is, what is H inverse and what is G inverse? That means inverse of a system. Now, what do we understand by inverse of a system? An inverse of a system would be such that if you gave some signal xt as the input, right? And then if you feed this into the inverse of that system, the output should again be xt. In other words, if we are looking at this whole setup of the original system followed by the inverse system, this should be an identity system. If this was an LTI system, we could have said that the impulse response of such a system should be delta t, but that can only be said if this was indeed an LTI system. But here it's not really given. Of course, for system H, you can see that it's an LTI system, but G is not time invariant. So that's why we'll not use this logic, but this is for your basic understanding of what is the meaning of a system being invertible. If such a system H inverse exists, then you can write the inverse of the system and you can say the system is invertible. Now in this question, it's quite clear that H is an integrator. So H inverse would be a differentiator. And in that case, you would be able to write that yt is d by dt of xt, right? Because given a system that integrates, in order to get the same signal that you gave as input, in order to get the same signal as output, you would need to differentiate it, right? So H inverse is simply derivative of xt. What is G inverse? You notice what G does? G basically compresses a signal in time. So what we need is a system that reverses this. That means a system that expands it by the same factor, right? That means something like this, scaling by a factor of half, right? This is again going to result in the same signal. That means G inverse in this case would be a system defined by input-output relationship as xt by 2. Moving to part B. Part B says, consider this system, which is made by cascading system H and system G. Find the inverse F inverse. So if this system together was considered as system F, we need to find and draw F inverse, right? So remember what H and G do. H is an integrator and G basically does time compression by a factor 2. Right? So in a sense, we are looking for a system. If this is H and G together, if this is system F, we are looking for something that actually reverses the effect of F, right? So if the input is xt, the output is still xt. Now, how do we do that? H is integrating the signal. G is compressing the integrated version by a factor of 2, right, along time axis. Now, to reverse this process, we need that first the effect of this time compression is cancelled because it is happening later, right? That means we would need a system like G inverse that does time expansion by a factor of 2. That means we've got this as an identity system, right? Whatever is the input, the same thing comes out as the output. And now we need something that cancels the effect of the system H. Right? That means we need H inverse. So if you look at it in a smaller frame, right? If you look at just this in itself is an identity system, right? So whatever comes in, the same thing comes out. So this is like there is no change in the input, and if there is no change here, and if you look at this larger picture, then right, H followed by a system which does not do anything to the input, followed by H inverse, this also should result in the same input xt, right? So in a sense we find that if this was system F as defined in the question, its inverse is actually going to be a system like this, where you have G inverse first, that is followed by H inverse, and this is what will be F inverse, right? So if we were to draw just F inverse, it would be G inverse followed by H inverse, right? This is how this inverse system would be defined. And we already know what is G inverse and H inverse. We've already defined that G inverse is basically a system that expands a signal by a factor of 2, and H inverse is simply a differentiator. Whatever is the input, it differentiates it. So this is how the system F inverse looks like. All right, and we've drawn it in terms of G inverse and H inverse. Moving on. Question 2 says that there are 3 systems defined in the following way. These are 3 discrete time systems. System 1 is this, system 2 is this, and system 3 is this. Suppose these 3 systems are connected in series, one after the other, right? Like as shown here in this figure. Find the input-output relationship for the overall interconnected system. That means we want to represent Yn in terms of Xn. All right. So let us define some intermediate outputs. Let us say the output of system 1 is some Wn, and let the output of system 2 be some Zn, right? And Zn serves as the input to system 3 that gives the output Yn. The definitions of these systems is already defined here, so let us just write that. So we know that Yn, what does it do? Third system, whatever is the input, it compresses it by a factor of 2, right? So the input here is Zn, so this is supposed to give us Z of 2n. Now, what is Z of 2n? Z of 2n is the output of system 2 when input was Wn. And what does this system 2 actually do? This operation, right? Where input is Wn. So let us rewrite this. So we could say that the same thing, but wherever you have n, we would write it in terms of 2n, right? So in terms of W, we could say that this is W 2n plus half W 2n minus 1 plus 1 by 4 W 2n minus 2, right? We're writing output in terms of Wn, but instead of Zn, we need to write Z2n. So we are just replacing the argument everywhere with 2n. Now going backwards, what is Wn? Wn is the output of system 1 when input was Xn. So if I was to write this in terms of Xn, what would I do? I'll have to look at this, right? And what does this system do? It gives output Xn by 2 when n is even and 0 when n is odd, right? So of course, when argument is 2n, this is an even number. And for this, you would get x of n. For the second term, looking at this argument, this is obviously odd, and therefore you would not have this term actually as an output of system 1. Right? And this term, you could have written this as 2n minus 1. And then when you would be doing x of n by 2, this 2 would get cancelled and you would get 1 by 4 x of n minus 1. So this is your answer. This is the input-output relationship that was asked in the question. Next part of this question is this system linear? Is it time invariant? Now, we've already covered linearity and time invariance in a previous tutorial, so I would leave that to you for you to find that this system is indeed linear and time invariant. Okay, how? Please derive it yourself. Part B says consider a second series interconnection of the form question 2. That means you've got the same kind of a system 1, system 2, system 3 connected, but this time the definition of these systems is different. This is how system 1 is defined, this is how system 2 is defined, and this is how system 3 is defined. In this case, the question says find the input-output relationship like we just found before. And now we also have to find the conditions of ABC. A, B, and C are these constants, which are a part of system 2 basically. We need to find which conditions are needed on these numbers so that the overall system either is linear time invariant, it is identical to system 2, and if it is causal. So let's take it one by one. So let us first start with the input-output relationship. Let's do the same exercise again. I'll keep the intermediate output still as Wn and Zn, and I'll just quickly redraw it here. We follow the same process. Yn would be what? Given Z as the input, what does system 3 do here? Just a reflection, right? So Yn is simply Z of minus n. Now, what would be Zn in terms of Wn? Zn in terms of Wn, whatever is that value, we've got to reflect n instead to minus n. So wherever there was a n, we've got to write minus n. So we could write that as if a w, it does n minus 1, right? So but we're writing z of minus n, so we'll write w minus n minus 1 plus b x of, instead of n, we will write minus n plus c x of minus n plus 1, right? Because we are writing z of minus n. Now we go backwards. How to write w in terms of system 1 xn? What is the relationship? This one, right? It is again a reflection. However, this time note that whatever is the argument has to be reflected by minus 1, right? So this time we can say that this is equivalent to saying a of x. So this could have been written as minus of n plus 1. This could have been written as minus of n minus 1. And now that we are writing in terms of system 1, we could have said that this is a times x of minus of this term, that is n plus 1, plus b times x of n, minus of n, plus c times x of minus of this term, that means x of n minus 1. Okay. So this is how you've defined yn and xn, input-output relationship. Now the part says we have to find conditions on A, B, and C such that the overall system is linear time invariant. So for this system to be linear time invariant, you'll be able to show that no matter what are the values of A, B, and C, this system always remains linear time invariant, right? So for part 1, you can say the system is LTI for any choice of A, B, and C. The second part asks, what should be the relationship so that the overall system, that means this relationship, is identical to that of system 2. What was the output of system 2? This, right? So if we compare the outputs of system 2 with the overall output, we notice there are certain similarities. So there is this some constant times x of n plus 1, some constant times x of n plus 1. Some constant times x of n minus 1, constant times x of n minus 1 here, then a constant times xn and a constant times xn. So what is the major similarity that we notice for these two to be similar, for these two to be identical, is that we notice that B is still B in both the cases. If A was equal to C, right? If A was equal to C, that means this is C and this is also C. In that case, we could have said that the two systems are identical. So the answer for the second case is the condition being A equal to C. The third case says, what is the condition that the overall system is causal? Now, what is the meaning of a causal system? A causal system is non-anticipatory. That means the output of a causal system depends only on the present and past inputs. It has got nothing to do with future inputs. So if we again take a look at the overall system, we notice that there is one particular term which is dependent on future inputs, that is this, right? And if we could get rid of this particular term, we can reduce this system to a causal system. And how do we do that? If A was equal to 0, we would not have this term which depends on future inputs. And as a result, the overall system can be made causal. We now move on to question 3. Question 3 says, consider the following system. So LCCDE stands for linear constant coefficient differential equation or difference equation. Right? Now, this is a simple mathematics question. The relationship between input and output being yt and input being xt, is given to us in the form of a differential equation, a linear constant coefficient differential equation. Input is also given to us, and we need to find the family of signals yt, that means a set of solutions that satisfies this homogeneous equation, right? So how do we approach such questions usually? For such questions, we would usually assume, we'll start with the assumption. We will say, let us assume that yt is of the form some a e to the power alpha t, right? And then we substitute this yt in this equation, which is known to us. And when we do that, so we're basically saying derivative of yt, that means a alpha e to the power alpha t, this is dy by dt, plus half of yt, so half of a e to the power alpha t. This is equal to xt. What is xt? E to the power minus t ut. Now, what do we know about this e to the power minus t ut? We know that it is a decaying signal and it's a right-handed signal, okay, because it's multiplied by ut. What do we know about it? If we were to assume that ut is undefined at t equal to 0, or its value is 0 at t equal to 0, then we would say this term is equal to 0, right? So at t equal to 0, plugging in t equal to 0 everywhere, we would have got a alpha into 1 plus half a is equal to 0, right? That means a alpha plus half is equal to 0. Now we know that output is not equal to 0, right? That means a cannot be 0. If a was 0, then output was 0, and that's not the case here. That means it is this term that needs to be 0, which tells us that alpha is minus half. And if alpha is minus half with a not equal to 0, that gives us a family of solution yt of the form a e to the power minus t by 2. A e to the power minus half t, plugging in alpha equal to half. Okay. So this is a family of solutions that we are looking for. The next part says, Assume that for t greater than 0, one solution with xt as specified is of the form this. So, right? So given this, so assume that for t greater than 0, one solution is something like this, one particular solution. For this, determine the value of a. That's the question. So what do? It is given that this is a possible solution. So we will be substituting this solution for t greater than 0 into the differential equation. If this is a solution, it should satisfy this relationship, right? So we'll plug in this yt. So we're basically saying that this d by dt of yt plus half yt equal to xt. When you plug in this possible yt, it should still result in xt, right? So we need to determine the value of a for this condition. So let us plug in. So you would get, for the first term, you would get minus a e to the power minus t, right? Derivative of this, plus half a e to the power minus t. Remember what is xt? E to the power minus t ut is xt. For t greater than 0, we know that this signal is simply equal to e to the power minus t, right? Because ut is equal to 1 for t greater than 0. So I'm going to write e to the power minus t here. And we've got e to the power minus t everywhere, which can cancel out on both sides. And we would get minus a plus half a is equal to 1. And this gives us a as minus 2. This was the solution for part B. Part C requires us to show that this particular y1t, this particular form of output, is one solution for all t. Okay, so we do the same process again, and we already have the equation ready with us. And now this is the y1t that we need to plug in here and see whether this actually results in xt. Right? So we have to show that this is actually a solution. So what do? We can write this in steps. So let us write the first part first, say just this term. So d by dt of y1t, this would be equal to what? This would be, note that we are talking in terms of ut. That means, see, there are different ways of defining ut. Normally, the most popular way to define ut is to say that it is undefined at t equal to 0, and its value is 1 everywhere else and 0 everywhere else, right? However, it appears that in this solution, it's taking the value at t equal to 0, 0, right? Another very popular way of defining ut is to say that its value is 1 at t equal to 0. So here it seems that as per the solution, at t equal to 0, ut is equal to 0. So we are going to proceed with that, right? And if that is the case, we could say that for t greater than 0, for t less than 0, it's going to be 0, obviously. But for t greater than 0, we just write the derivative of this term. So it is 2 into minus half e to the power minus t by 2 minus 2 into minus 1 e to the power minus t, right? This is just the first term. If we added the second term as well, that means we're saying d by dt of y1t plus half y1t. Now, half of y1t means this 1 is going to cancel both these terms, and we will simply be left with, first, I'll write the first part. So that becomes, right? And the second part simply becomes e to the power minus t by 2 minus e to the power minus t. This is for t greater than 0. And it's 0 for t less than equal to 0, right? So this basically means that these two terms are going to cancel out, and 2 minus 1 is just going to leave us with e to the power minus t, right? So this is simply e to the power minus t. And this is, as per this solution's definition of ut, is nothing but e to the power minus t ut, right? Which is nothing but xt. That means that substituting this yt actually satisfies this differential equation, and therefore this is one solution of the system for all t. Moving to question 4. Consider this block diagram that relates two signals x and y, and we need to assume that the system described by this figure is causal and initially at rest. That means initially there is no output for any input, there is no input rather, and that the fact that it is causal. So when we say a system is causal, we're basically saying that the output will be 0 unless a non-zero input is applied, right? The name causal itself says that it is cause dependent, like until there will be an input, there will be no output, right? Now, given that, we need to determine the difference equation relating yn and xn. So we basically need to just find the relationship between yn and xn. So as this question says, this D stands for a delay. That means if this is yn, then yn delayed by 1 unit should be the output here. So this would be y of n minus 1. If this is yn, output would be y of n minus 1. And this shows that we are multiplying this yn minus 1 with a scalar minus half. And that is what is getting added here, right? So the output here is what? It is xn minus half y of n minus 1. This is what is coming here, and this is actually what is yn. So if I was to write yn, I would simply say yn is xn minus half y of n minus 1. Now, typically the practice would be to keep all y's one side and x the other side. So we could say yn plus half yn minus 1 is equal to xn. So this is the relationship we are looking for in part A. Part B says, without doing any calculations, determine the value of y minus 5 when xn is un. Xn is a unit step function in discrete time. So it's something like this. This is how un looks like, unit step function. Now, it's given already in the question that this is a causal system. And we know that if a system is causal, it cannot have an output unless a non-zero input has taken place. And because the input is un that starts only at n equal to 0, we know that at n equal to minus 5, there is no input, because at minus 5, the value is 0. Right? So there's no calculation needed, and we can simply say that because the system is causal, y of minus 5 will be 0. Now the next part says, assume that a solution to the difference equation in part A is given by this form. Okay, so this is an assumption that we are going ahead with. And when input xn is delta n, what is delta n? This is delta n. Given this, we need to find an appropriate value of k and alpha and verify that yn satisfies this difference equation. Okay, so the potential value of the solution is given, and we just need to verify it and also find an appropriate value of k and alpha. So let's plug in these values. Again, a few things that we know. When we are doing this kind of an operation and we are talking about all possible values of n, right? So we're looking at all possible values of n. That means what will be the case when n is less than 0, what will be the case when n is equal to 0, and what will be the case when n is greater than 0. Now, because the system is causal and the input is a delta function whose value is 1 only at n equal to 0, that means nothing before it. That means it's by default known that yn for n less than 0 will be 0. There'll be no output because there is no non-zero input at that point. At n equal to 0, what do we know? Let us plug in the value. What is the equation also? Let us write the equation that we just got in part A. This equation, let us copy it down there. This is the relationship we had. So for n equal to 0, this means y0 plus half of y0 minus 1, y minus 1 is equal to xn. And what is xn? Delta n. And at n equal to 0, delta n is equal to 1. Okay. So what are we trying to write? We are trying to plug in this value of y in this equation. Okay. So what would we get? We would get k alpha to the power n un plus half k alpha to the power n minus 1 un minus 1. This is equal to delta n. This is the equation we have. And now we are looking for different values of n. So particularly talking about n equal to 0, when I plug in n equal to 0 in this expression, I would get k alpha to the power 0 u0 plus half k alpha to the power 0 minus 1 u of 0 minus 1 equal to delta of 0. We know that delta of 0 is equal to 1. We know that u of 0, the value of un, this unit step function, at n equal to 0 is also 1. So we plug in this value. So we've got k alpha to the power 0 is 1, k into 1 plus half k u of minus 1. U of minus 1 is 0. So this term has become 0. This is equal to 1, which tells us that k is equal to 1. Right? Because u of minus 1 is 0. Remember, u is unit step function and delta is unit impulse function. Right now we're talking in terms of discrete domain. This is for n equal to 0, and then what happens for n greater than 0? Let's write that expression again. This one. So let me just rewrite for delta n as the input. It would be easier. So we are basically saying yn plus half y of n minus 1 is equal to delta n. But delta n for n greater than 0, like for n equal to 1, 2, 3, and so on, for n greater than 0, delta n is equal to 0. This is the equation we're looking for now. We plug in yn. Yn is k alpha to the power n un. We know that un is equal to 1 for all n greater than 1. So I'm just going to leave a 1 here. We also know that k is equal to 1. We just found out, right? So alpha to the power n is the first term plus half of yn minus 1. What would be yn minus 1? K, that is 1 times alpha to the power n minus 1 u of n minus 1. Now, because we are talking about n greater than 0, un minus 1 means value of un shifted to the right hand side by 1 unit. Right? This is u of n minus 1. So since we are talking about n greater than 0, that means n equal to 1 onwards, we know that this term is still equal to 1, right? So we can still get rid of this, say it's 1 equal to 0. So this is basically the relationship we've got. Alpha to the power n plus half alpha to the power n minus 1 is equal to 0. Now alpha to the power alpha raised to n minus 1 basically means alpha to the power n by alpha. And we could say this is like saying alpha raised to n 1 plus 1 upon 2 alpha. This equation. Now alpha to the power n cannot be 0, right? It's an exponential. That means it's this term which will have to be 0. And this tells us that alpha is nothing but minus half. Right? This is another thing we had to find. The question said find the value of appropriate value of k and alpha. And then we also need to verify whether this satisfies this relationship or not, right? We have to verify that yn satisfies the difference equation. So let us plug in with these values of alpha and k that we've just found. Let us plug this in back into our original expression and see whether you actually get xn or not. So in other words, we've got yn as k alpha to the power n un, and we've just found the value of k as well as alpha. So k times alpha to the power n un, this is yn, right? So we need to verify whether this yn plus half y of n minus 1 actually results in xn, which is delta n. So let's plug in these values. This plus half of minus half to the power n minus 1 u of n minus 1, right? So half y of n minus 1. Wherever you had n, you're writing it as n minus 1. Now, so what this basically means is minus half to the power n divided by minus half, right? That is what minus half to the power n minus 1 means. And these two can get cancelled, and you've got a minus sign left outside, which means that I could just simply take this out, and this is nothing but un minus u of n minus 1, right? And what is this? Un minus u of n minus 1. Let's look at it graphically. This is how un looks like, starting at 0. And this is how u of n minus 1 looks like, starting at 1. So when you subtract the two, you get rid of all these, and you're only left with a 1 at n equal to 1, and which is nothing but delta n. So this is nothing but minus half to the power n delta n, and delta n has a value 0 everywhere where n is not equal to 0. So it doesn't matter, right? What is the value of n? It's defined only for n equal to 0. So you could simply say that this is equal to 1 for n equal to 0, and this is equal to 0 for n not equal to 0, right? Or otherwise. And this is nothing but delta n, and that is what was the input xn, and hence we have verified this relationship. Part D says that we need to verify our answer to part C by directly calculating y1, y0, y0, y1 and y2. So let's do that as well, right? So we already know that yn plus half y of n minus 1 is equal to xn. Now, since I want to get yn, I'm just going to take it to the other side like this. And we also know that xn is nothing but delta n. So I'm going to plug that in. And we also know that y of minus 1, right? We need some starting point. That means because this is a causal system, we know that yn is equal to 0 for n less than 0. That means y of minus 1 is 0. So let's start with that. So y of 0 would be what? Minus half y of minus 1 plus delta 0, right? And this is equal to 0. That means this is equal to 1. All right. Y of 1 would be what? Minus half y0 plus delta 1. We know that delta 1 is 0 and y0 is 1. That means this is minus half. What is y2? Y2 is minus half y1 plus delta 2. We know that delta 2 is 0. Y1 is minus half. So minus half into minus half is 1 by 4. So is this what really yn was? Remember what yn really was? Yn was k alpha to the power n un. And we just found that k was 1 and alpha was minus half. So is this what you really get when you plug in different values? Because you have a un multiplied. Of course, you have all y n equal to 0 for n less than 0. That means n less than equal to minus 1, right? So how does yn look like? At n equal to 0, its value is 1. At n equal to 1, its value will be minus half to the power minus half to the power 1, that is minus half, right? At n equal to 2, its value is going to be 1 by 4, positive, and so on, right? So this verifies our solution from part C. That was about this tutorial. I'll see you next week. Thank you.